The OSI model. It is the most referenced protocol model in the industry today, and still, none of today's popular network protocols follow it directly. Today, we're going to look at the OSI model and start by defining what it is. Next, we're going to look at layered communication and the advantages that it offers us. We're going to look at the different layer responsibilities within the OSI model, and finally, we're going to cover data encapsulation. What is the OSI model? It is an abstract reference model developed by the International Standards Organization, ISO, in the early 1980s. The reason the ISO decided to develop this model was that IBM, through SNA, was cornering the market, and they wanted to keep it competitive and keep their foot in the market. So they said, let's standardize as a whole and keep everybody somewhat level. Now, the OSI reference model, as it says here, is simply a guide to network protocol development. What we have is 7 layers: the application layer, the presentation, the session, transport, network, data link, and physical. Remember, in its entirety, this is simply a guide. When we take this guide and apply it to a real-world protocol like TCP/IP, we see similarities. The application, presentation, and session layers, all 3 of these are combined into what is known as the application layer. The transport layer maps directly across. The network layer does as well. And in the final 2 layers, the data link and physical layer map to the physical layer of the TCP/IP stack. Let me take a step back and define for you what a network protocol is. I have a computer here that I'm going to label N1 for Nugget 1. I also have a distant computer that I want to communicate with that I'll label N2. Each of these computers have a user in front of them. Let's say that these users are running a chat program. What happens is I have an application layer here that is a GUI, a front end for this person to view and to type in information and hit enter. Once I hit enter, the transport, the network, and the application layers take care of this data and get it ready to be transmitted over a physical medium, the cables that are connected to your PC, over to the other PC, where these first 3 layers are going to reconstruct the data so that it is viewed by this individual exactly as I typed it in here. And now everything I typed in here was sent across, rebuilt here for his viewing pleasure. I have included this discussion on TCP/IP and its model just to give you a reference or a big picture sense and ground you into what we're talking about when we're introducing the reference model. But keep in mind, this section covers the OSI model, so that will mean that we will discuss each layer and the responsibilities associated with each layer, even though they're not particularly applied in their entirety in the real-world scenarios like TCP/IP or the network protocol. Continuing our definition of the OSI model, we find that the OSI model also is a reference model, which we knew already, for layered communication in a networked environment. So this is what's new to us, layered communication. Let's discuss what that is. We'll start by taking a look at the first rule of layered communications, and that is each layer provides a standard output to the layer below and facilities for use to the layer above. What does that mean within our model? Let's look at the presentation layer. That means that it's going to provide a standard output to the session layer and facilities for the application layer. By facilities, we mean choices or categories for the data put in at the application layer to be funneled through in the presentation layer. So that's easy when I'm talking about a layer that has a layer above it and below it. But what about the application layer? While you can see that it might have a standard output, and it does, to the presentation layer, what facilities does it offer to the above layer? That's when the user comes into play. Understand that the application layer is simply the GUI, or the graphical user interface, or the front end for this user's viewing, and it also can be the options within that program. That takes care of the top 3 layers and the fact that they are user-facing. But what about the bottom 4? We say that the bottom 4 layers, the transport, network, data link, and physical, are network-facing. In other words, their job is to prepare the input data by the application for transmission over the physical medium. The OSI model was built on layered communication because of the advantages that it brings to the table. Namely, we have 4 listed here. First of all, divides the complexity of internetworking into discrete steps. Could you imagine trying to design a network protocol and having to address the user interface, develop a data format, build acknowledgments, recovery, and routing options within it, as well as define a protocol for transmission over the physical media? That would just be too much to ask. Because it divides the complexity of internetworking into discrete steps, if you develop the user interface, everything below that as far as data formatting, acknowledgments, and routing will take care of itself because you will just provide your user interface a standard output out of that to the next layer. Sounds much easier, doesn't it? All right, the next one. Allow standards-based software development. A good example of this is IPsec, which is the IP security protocol that was developed. What we have is within the IP stack, we have a funnel that looks like this. On the top of this funnel, we have many applications, FTP, Telnet, TFTP, and the list goes on. Then at the transport layer, we have two options, TCP or UDP. Finally, at the network layer, everything is IP. So what the IPsec protocol was able to do was standardize based on this model and say, we're going to encrypt right here at the network layer. Make all the applications come to us. Instead of having to write security encryption for each type of application here, they simply said, let the data come to us, and we will write an encryption model right here in the middle of the stack. The layered model also allows specialized development of modular software. A good example of this is going to be IP, which resides at a network layer. And underneath that network layer, I have many options for data link protocols. They can be 802.3, True Ethernet, HDLC, PPP, SLIP. I mean, the list goes on. But the beauty of layered models is that each of these modular type data link protocols can plug into IP because of the understanding of the standard output of the network layer to them and the facilities that they offer the layer above. Isn't that awesome? You can kind of get an idea of why our software today is much more powerful than before they introduced the layered model of internetworking. Because before you had to develop so much more. Now you can spend more time on the bells and whistles and the actual functionality of the application without having to worry about the transport and how that data is going to get across the network. Let's look at the next bullet. Enables peer-to-peer communication on a per-level basis. To explain that, let me bring up two PCs, as we've done in the past, N1 and N2, each having 7 layers below them. The application layer is where Telnet resides. As a user on N1, I'm typing in commands. Now those commands are not executed on my local machine, and they're not executed on the wire, and they're not executed within the stack on N2. They're executed at the application layer on N2, which helps development as well to know that input here equals output here without having to address the traveling of up and down the stack. There are many more advantages to the layered communication model, but these are the most noteworthy. All right, so far we've looked at what is the OSI model. We've also talked about layered communications and the advantages of layered communications. Next, let's look at the layered responsibilities. What that means is we have each of our layers here on the side, starting with the top, number 7, application, presentation, session, transport, network, data link, and physical. Now we're going to look at what is each layer supposed to do. First of all, application. Used for applications designed to run over a network. As we said, applications running from one computer to another. So over a network, the application layer is used for that design and that user interface. Presentation. Responsible for data conversion formatting. At this layer, this is where you'll usually see data formats like GIF or TIFF or JPEG, those types of formats as options. The session layer establishes, maintains, and ends network sessions across a network. Again, it's important to say across a network because it's from one computer to another. An example of this is NetBIOS. Their naming and their session commands. Both are examples of session type work and responsibilities. The next layer is the 4th layer, the transport layer. This layer manages flow data through windowing, acknowledgments, and error recovery. Understand, this session layer sounds like flow control. And it is, but it's the flow control of the conversation, the starting and the ending of the conversation. The transport layer is about flow control of the data. And so that's segments of data that we're going to transmit because These top pairs up here are user-facing, up to here, and options in the programs for use. Once we hit the transport layer, we're looking downwards and saying, how am I going to get this information to computer? Another responsibility of the transport layer is to divide raw data streams into segments. Understand that if we're using, let's see, a user program of FT, we want to transfer a file from one computer to another. This file can be very large. We can't transmit it all at once because of the limitations on the physical media down here and the size of the packets that it can transfer. So what transport layer does is it makes sure it puts that bulk data into individual segments that can be transported over physical medium. Kind of like a scene from an Old West movie. In the town, you have a building burning here, and of course on the other town, you well. Now what you would like to do optimally is take all the water well, deliver it fire, put it out. But realistically, you have people in this path, and they can only carry so much. Again, the limitation of the physical medium. So you have to have buckets of water right here transferred from person to person and thrown on the fire. Eventually, you will get the job done. You will have this whole FTP file transferred to another machine, but you have to understand the limitations of your physical medium. The network layer has many responsibilities. The first one is responsible for end-to-end delivery packets across the network. End-to-end delivery. What I've done here is I've included two protocols that reside at this layer just so you get an idea of what they do. IPX and IP, what is done at this layer. So it's saying from N1 to N2, responsible for the delivery of this packet. It doesn't matter that these computers are right next to each other on the local area network or across the world over 14 hops or 14 routers. I am still responsible for end-to-end communication at this layer. I also define the local addressing to make that happen. Because if I have a starting point and an ending point, I have to uniquely identified. And that's what our logical addresses will do. As in the case of IP, and you might see out there is 192.168.1.2. That's the logical addressing that we're talking about. Another function, fragments packets based on the differing MTUs. We talked about the limitation of the physical medium down here. As you go from network to network, let's interject routers here. Each router connects to network. And these physical mediums will change. If I have Ethernet here, FDDI here, SLIP here, and fast Ethernet here, each one of these can have a different maximum transmission unit. That's what an MTU is of the packet. Basically, it's just saying how large can this packet get? It's max. Because these differ, you might send a packet from N1 at a size of 1500, get to the slip link, have an MTU of 552, which is smaller than 1500, and have to take this one packet, divide it into 4 packets, and send it its way. That's called fragmentation, and that's at this network layer as well. And finally, convert segments to packets. What are we talking about here? Basically, we started with a bulk of data in the application user interface. The segmented that into smaller, more manageable pieces. The other thing it did that we didn't mention there was connect a header in front of each segment. And header helps the transport layer on N2 know what to do to segment. You got to remember, peer-to-peer communication. N1, any instruction given at the transport layer will be instructions for the transport layer of N2, not any layer beneath it on N1 or beneath that transport layer on N2. So there's specific instruction in the header. The same thing for the network layer. When it has the same data segment that was at transport, complete its header, it adds a header of its own because it had instructions for its peer on N2. Now we call this new data form a packet. Up here it was called a segment. The idea of adding specific instructions at each layer to the original data so it can be communicated to the distant end at its peer level is called encapsulation. And it's something we'll cover in more detail later in this series. So let's move on to the data link. Data link defines the protocols used to transmit and receive data on the physical medium. Examples of protocols at this layer are 802.3, ATM, FDDI, and the list just goes on. Basically what we're doing here is we're framing the output that came from the network layer so that it can be physically moved over the physical medium to the distant end. Once the frame is completed, we move into the next layer that defines the physical and electrical characteristics of the transmission medium. we're really talking about here is the connectors, the cables, the encoding, and the voltage involved with this layer. So there you have it, the 7 layers and the responsibilities at each. There's a lot to take in, so what I've done is worked up a model to represent each of the layers. First of all, the our teenager is met his grandparents. OSI model made easy. Right. So far we've looked at the OSI model, what it is, communication